Today, we're going on a bit of a journey. We're heading deep, deep underground into a world that, to you and me, looks completely solid, but it's actually hiding a liquid treasure. In this explainer, we're going to uncover the secret life of reservoir rocks.
All right, so let's just get right into the biggest question. Take a look at this. It's a core sample, basically a big cylinder of rock pulled up from thousands of feet down. And it looks like a rock, right? It's solid, it feels dense, you can't see any holes in it, and yet this is where oil and gas come from. So the central puzzle we're going to solve is, how in the world do you get liquid gold out of what looks like solid stone?
And that question right there, that brings us to what we can call the solid rock paradox. Because what our eyes are telling us is one thing, but the reality, deep underground, is something else entirely.
I mean, seriously, to the naked eye, there are no openings, no cracks, nothing. If you poured a glass of water on this thing, it would just roll right off. This is the exact puzzle that had early geologists scratching their heads, and it's the first big myth we've got to bust. The treasure isn't inside the rock in the way you might think.
So to really see what's going on, we have to zoom in. No, I mean way, way in, because this solid-looking piece of stone is actually hiding an incredible microscopic storage system.
Let's try a little thought experiment to get our heads around this. Imagine you take a bottle and you fill it all the way to the top with sand. It looks pretty full, pretty solid, doesn't it? But you and I both know there are tons of tiny, empty spaces, air, between every single one of those sand grains.
Okay, now let's fast forward a few million years. Under immense pressure, minerals act like a kind of cosmic glue, fusing all those sand grains together into solid rock, like sandstone. But, and this is the amazing part, that whole process doesn't crush those little spaces. It actually locks them in place. It preserves them.
And that, right there, has a name. It's our first huge concept for today, porosity. We're not talking about big caves here. These are microscopic voids, teeny tiny little storage units, all connected together. And that's where the oil, the gas, and the water are actually hiding.
So the best way to think about this rock isn't as a rock at all. It's a stony sponge. I love that description. It's a totally rigid structure, sure, but it's filled with these microscopic holes just waiting to soak up and store fluids.
Okay, great. So the rock can store fluid. That's porosity. Got it. But, that's only half the story. Because if all those little storage units aren't connected to each other, then the oil is trapped. It's not going anywhere. You need more than just storage. You need highways.
And those highways, they have a name too. That's our second key term, permeability. This is all about how connected those pores are. It's a measure of how easily fluids can travel through the rock, zipping from one tiny storage unit to the next through these little corridors. Honestly, without permeability, porosity doesn't really matter for getting oil out of the ground.
And boy, does it make a difference. You can think of it like this. You've got your stingy rocks, like shale, which have low permeability. They hold on to pressure and release fluids really slowly. But then you have generous rocks, like sandstone. They have high permeability. They can release their fluids and pressure incredibly fast, sometimes so fast that it gives drillers almost no time to react to a kick, which is basically an uncontrolled surge of fluid up the well.
So if you want a simple way to remember it, think of it like this. Porosity is storage, but permeability, that's speed. It determines how fast things can flow, which can be the difference between a successful well and a total disaster. All right, so we've figured out how fluids are stored and how they move, but there's one more major misconception we have to tackle, and it has to do with how all these different fluids are actually arranged down there in the dark.
I'm sure you've seen diagrams like this before, right? It looks like a perfect layer cake. You've got gas on top, because it's the lightest, then oil, then water on the bottom. It's neat, it's tidy, and at the microscopic level, it's totally wrong.
The truth is actually a lot messier and, frankly, a lot more interesting. Here's the shocker. There's really no such thing as a 100% oil zone. In the exact same pore, the same tiny storage unit, you will find both oil and water living side by side. So how on earth is that possible?
Well, it all comes down to a really cool scientific principle called wettability. Think of it like a sticky force. Here's the story. Millions of years ago, before any oil showed up, these rocks were completely filled with water. When oil started to migrate in, it pushed most of that water out of the center of the pores. But it could never push all of it out. A super thin film of that original water is still there, stuck, clinging to the surface of the rock grains.
A brilliant way to think about this is that water is the owner of the house. It was there first. The oil is just the tenant. The oil might fill up most of the room, but the owner never leaves. They're always there, clinging to the walls. And that's why you can drill into the very top of a productive oil zone and still find water.
Okay, so stony sponges, homeowners, tenants, you might be wondering, why does all this microscopic detail matter so much? Well, it matters because understanding this hidden world is the absolute key to being safe and successful out in the real world.
See, as a drill bit plows through the earth, it goes through what are called transition zones. These are areas where that mix of oil and water is constantly changing. And as that mix changes, the density of the fluid changes. And that can totally mess with the very delicate pressure balance, the hydrostatic balance, that a drilling team needs to maintain to keep the well under control.
This is where it all comes together in what's called defensive geological action. It's pretty amazing teamwork. The geologist, who understands all this stuff, is like a lookout. They see a stingy, low-permeability rock on their sensors, and they know it's bottling up pressure. So they warn the drilling team, hey, get ready, a generous, high-permeability rock is right after this. And that warning gives the team time to prepare and manage that sudden release of pressure, preventing a kick.
So let's just boil it all down to the three big takeaways, right? Porosity is the rock's storage space. Permeability is the speed at which things can move through it. And water, well, water is the original inhabitant, and it's always there clinging to the house.
And that's really the bottom line. Putting these three concepts together, understanding them, it's not just some academic exercise. It's what separates a safe, productive operation from a potential catastrophe. It all comes down to knowing what's going on in the invisible world inside a chunk of solid rock.
It's pretty wild when you think about it, isn't it? That rock we started with that looks so simple and solid, it's actually a complex sponge, full of invisible highways, with a whole history written in oil and water. Which kind of makes you wonder, what other invisible realities are out there shaping our world right under our noses?